Welcome to the Crazy Hat Chemist. So here we go. Today is empirical formula calculations, the third one in this subset. And we've been talking about stoichiometry and dimensional analysis, so let's get moving on with empirical formula calculation. So hold on to your seat. Here we go. Bam! Okay. Rubbing alcohol, aka isopropanol or isopropyl alcohol, is used in medical offices to sterilize the surface of the skin prior to injections. A combustion analysis is performed on 0.255 grams of isopropanol, 0.561 grams of carbon dioxide, and 0.306 grams of water is recovered through this analysis. Determine the empirical formula of isopropanol and from the combustion analysis. So here we go. This is a combustion problem here. So isopropanol is a hydrocarbon. That is carbons, hydrogens, and oxygens. We are trying to solve for the X, the Y, and the Z. Those stoichiometric, or rather whole numbers of X, Y, and Z will give me my formula for isopropanol. We know it's a combustion, so we have the addition of oxygen gas on the reactant side, and a complete combustion. That means that I have carbon dioxide and water on the product side. We can't balance this because we actually don't know the formula for the isopropanol right now. So I'm going to step you through a thought process and see how this problem goes. So first of all, we have 0.255 grams of the isopropanol that we're going to combust. Okay? And then we got to figure out what we're going to do with this. So number one, the mass of the carbon is all in the carbon dioxide. So the here's the carbon, and it's going to go all to the carbon dioxide. You see that the other formula on the product side is water. There's no carbon in that. So that means all the mass of the carbon in the isopropanol goes directly to the carbon dioxide. And how much carbon dioxide do we have? 0.561 grams. Okay, number two, the mass of the hydrogen is all in the water. So here's the hydrogen in the isopropanol, and all of this hydrogen goes to the water because there's no hydrogen in carbon dioxide. So how much hydrogen do I have in the water? Well, I have 0.306 grams of water, and I need to figure out how much hydrogen I have from that. Then, the mass of the oxygen is determined from a mass difference. Now, remember the key words there are mass difference, and that's a subtraction problem. I have the total mass of 0.255 grams of the complete isopropanol reactant, and I'm going to figure out how many grams of hydrogen, how many grams of carbon, and then from that, I will get a mass of oxygen. So, here we go. Next slide. Bam! There's the same problem right there, just a little bit smaller, just so that you can see it on the same page. So the mass of the carbon is all in the carbon dioxide. So what we're going to do is we're going to take the 0.561 grams of carbon dioxide and convert that into grams of carbon. So grams of carbon dioxide, you're going to use the molar mass for carbon dioxide to get the moles of carbon, and then a mole ratio between carbon dioxide and carbon, and then the moles of carbon to get grams of carbon. I want you to pause the video and do that stoichiometry problem on your own. Here we go, unpaused. So here's that stoichiometric problem here. I got grams of carbon dioxide, the molar mass of carbon dioxide. I'm going to get moles. It's a 1-to-1 mole ratio. So if you look at the formula for CO2, carbon dioxide, how many carbons do you see in there? 1. Therefore, it's 1 mole of carbon. And then the molar mass of carbon. And there's that number. So I have 0.153 grams of carbon in the isopropanol. Okay? All right. Number two, the mass of hydrogen is all in the water. So I'm going to start off with the 0.306 grams of water, and I'm going to convert that into moles of water. Then from moles of water, I'm going to get moles of hydrogen. But be careful and look at the moles of hydrogen in the moles of water. And then I'm going to convert those moles of hydrogen into grams of hydrogen using the molar mass. And here's that here. So I want to highlight something in yellow here, so pay attention to this. Where's that 2 moles of hydrogen coming from? It's coming from H2O. Okay? That's unlike the carbon dioxide where there was just 1 carbon. This is a number right here, and that's 0.0342 grams of hydrogen that is in the isopropanol. Okay, so step number 3. The mass of the oxygen is determined from a mass difference. So I need to actually sum up the mass of the carbon, the mass of the hydrogen, to get the mass of a hydrogen and carbon within the isopropanol. I have the total mass, So that's what this is going to be. I'm going to sum these up. So that's 0.187 grams of carbon and hydrogen in the isopropanol originally on the reactant side. So how much isopropanol do I have? 0.255 grams of isopropanol. So I'm going to take the 0.255 grams, do a difference, that is a mass difference, and that is a subtraction with the 0.187 grams of carbon and hydrogen summed up. This will get me the mass of oxygen. So I'm going to take this difference here, that is the mass of that original reactant, which is the isopropanol, subtract the hydrogens and carbons from it, and I get the mass of oxygen. Okay? So now, thus far, what I have obtained here is 0.153 grams of carbon, 0.0342 grams of hydrogen, and 0.068 grams of oxygen. So I have masses of all of the elements that are in the formula that I want to determine the empirical formula for. So now what I'm going to do is everything that drives an empirical formula problem is actually in the definition of an empirical formula. And that is, the definition of an empirical formula is the simplest whole number mole ratio. So what I'm going to do is I'm going to take the mass of carbon, mass of hydrogen, mass of oxygen, and convert them into moles of those respective elements. And that is right here, and here, and here. So notice that none of these are diatomics, these are all elements. That gets me these three values. So moles of carbon, moles of hydrogen, moles of oxygen, okay? And now what I'm going to do is I'm going to look at all these numbers here in moles. That's 0.0127 moles of moles of carbon, 0.0339 moles of hydrogen, and 0.00425 moles of oxygen. What is the smallest number? The smallest number is that of the moles of oxygen. So I'm going to divide all three of these numbers by the same number, and that is the smallest number. So you always divide by the smallest. So now I'm dividing by the smallest. Now I'm going to get what those values are from that division problem for each one of those. I'm looking in the 10th position. So that is the 0.9, and then I don't have a number because it's actually the number divided by itself, which is just a whole number. Okay? So you can either add or subtract a 10th, and then if you can do that and get a 0 in the 10th position, then you're good to go. So the 2.9, I'm going to add a 10th, and I'm going to get a 3. The 7.9, I'm going to add a 10th, and I'm going to get an 8. The 1 is already a whole number. I don't have to change that, so I leave that alone. So once I add the 10th to the 2 carbons and hydrogens that are necessary in those mole ratios, then I'm going to get these 3 values. That is 3 for the carbon, 8 for the hydrogen, and 1 for the oxygen. So now I'm going to look at my combustion problem right underneath my title of empirical formula. I'm going to substitute in for the X a 3. I'm going to substitute in the Y for an 8. And I'm going to substitute in the Z for a 1. And then I get this formula for isopropanol. You should go look up the formula for isopropanol, but it is C3H8O. Okay? That was hopefully a fun problem for you to do. I'm the Crazy Hat Chemist. Unfortunately, it's not my birthday today, but we can celebrate anyways. Now we have just finished empirical formula calculations. Now what we're going to do next time is do a molecular formula calculation. And that will all be based on the empirical formula. So I can't wait to see you next time.